Hello, welcome back to EEE101 Electrical Circuits 1. Today we will discuss how to apply nodal analysis to circuits containing voltage sources. When we learned nodal analysis in the last class, we considered only current source and resistance as circuit elements. And we developed a structure for the node equation where the currents of the resistances were expressed in terms of node voltages using Ohm's law, and the currents of the current sources are typically known, so we could easily write the node equation and solve the equations for the node voltages. However, with voltage sources, the situation is complicated. Let's see how. We considered this circuit. We have three voltage sources in this circuit. There are four non-reference nodes. If we look at node 1, there are two voltage sources connected. If we look at node 2, there is one voltage source connected. If we look at node 3, there is again one voltage source connected. We cannot express voltage source current in terms of voltages because Ohm's law cannot be applied to voltage sources, and there is no other way to express the current in terms of voltages. So if we want to write node equation at a node where a voltage source is, we do not know how to express the current in terms of node voltage. As a result, node equation cannot be written at a node with voltage source connected. We need to find out an alternate way to treat voltage source in nodal analysis. Again, we look at this circuit. Voltage sources in this circuit has to be treated as special cases. Depending on how the voltage source is connected, we can define different types of special cases. Let's see what are the different special cases that we will consider. First, we consider case 1. Case 1 refers to a voltage source which is connected between the reference and a non-reference node. If we look at the circuit, we find that Vs1 voltage source is connected between the reference and node 1, which is a non-reference node. So, Vs1 is an example of case 1. Then we have case 2. Case 2 refers to a voltage source which is connected between two non-reference nodes. Again, if we observe the circuit, this voltage source Vs2 is connected between node 2 and node 3. Both are non-reference nodes. So, Vs2 is an example of case 2. Then we have case 0. Case 0 involves a voltage source which is connected in series with a resistance. If we look at Vs0 between node 1 and node 4, it is connected as case 2. However, if we look at node 4, there are only two circuit elements connected, Vs0 and R3. So this Vs0 and R3 are connected in series. So Vs0, instead of treating the source as a case 2 between node 1 and node 4, we will treat it as case 0 between node 1 and node 3. We will not consider node 4, and we will treat Vs0 as case 0. It should be noted that in your textbook, there is no case 0. Your textbook has treated only case 1 and case 2. Actually, it is not essential to have case 0. Instead of case 0, we could treat voltage source Vs0 as case 2 if we had treated the node 4 as a non-reference node. The problem with treating Vs0 as case 0 is that then we will be having four non-reference nodes. By treating Vs0 as case 0, we got rid of node 4 and we have only 3 non-reference nodes. So use of case 0 allows us to reduce the number of non-reference nodes and reduce the number of unknown node voltages that we have to solve. This is the advantage of introducing case 0. Okay, now let's see how to handle case 1. In this circuit, there are two non-reference nodes, 1 and 2. Each non-reference node has 3 circuit elements, and we assign V1 voltage at node 1 and V2 voltage at node 2. At node 1, we have two resistances connected, but we also have a 100 volt source. This is connected between reference and a non-reference node. So this is an example of case 1. Because of the presence of this voltage source, we cannot write node equation at node 1 and we need an alternative way. What is the alternative way? Let's recall how the voltages in a voltage source are related. If we have a voltage source with value Vs, whose plus node voltage is Vm and minus node voltage is Vn, Vm minus Vn is Vs. This is already known to us. Let's apply the same principle to this 100 volt source. The plus node voltage is V1, the minus node voltage is 0, and the value of the voltage source is 100 volts. So V1 minus 0 is 100 volts. This is the equation that we get for node 1. We do not write any node equation at node 1. So what is the principle? The magnitude of the voltage of the node where a case 1 voltage source is connected is equal to the value of the voltage source. Why are we saying magnitude? Because if we had connected the voltage source with opposite polarity, in that case V1 would have been minus 100 volts. To include both possibilities, we generalize the statement by using magnitude of the voltage term. So we have obtained from this method that the voltage of node 1 V1 is 100 volts. Okay, let's proceed. At node 2, we have two resistances and a current source. We can write the node equation at node 2 in a straightforward way. For 50 ohms, the current is V2 by 50. For 10 ohms, the current leaving node 2 through 10 ohms is V2 minus V1 by 10. So these are the two currents of the two resistances. On the right hand side, the current source current 5 ampere is entering, so this is positive. If we solve these two equations, we get V2 equal to 125 volts. So this is the essence of case 1, that the magnitude of the node voltage is equal to the value of the voltage source. Now let's look at case 2. In this circuit, we have two voltage sources and we have three non-reference nodes. If we look at the non-reference nodes, we see that at node 2, there are only two circuit elements connected. Similarly, at node 3, there are also only two circuit elements connected. We now change our procedure for nodal analysis, and we now say that we do not assign node voltage to every non-reference node. We assign node voltage to only those non-reference nodes where three or more circuit elements are connected. In other words, if a non-reference node has only two circuit elements connected, we do not assign any node voltage. So we will not assign any node voltage at node 2. We will not assign any node voltage at node 3. We remove those nodes. If we now look at this circuit, this 12 volt source is in series with 4 ohms between node 1 and reference. This is case 0. Similarly, this 10 volt source is in series with this 2 ohms resistance between node 1 and the reference. This is also case 0. Both the voltage sources are case 0 in this circuit. The advantage of treating case 0 is that the voltage source and the resistance are in series, so they are carrying the same current. We cannot apply Ohm's law to the voltage source, but we can apply the Ohm's law to the series connected resistance. So by looking at the series connected resistance, we can find out the current of this branch or this branch in terms of node voltages. So the main essence of case 0 is we apply Ohm's law to the series connected resistance. Let's see how this is done. To apply Ohm's law to the 4 ohms resistance, I need to know the voltage of the intermediate node. The voltage of this node minus 0 is 12. So this voltage is 12 volt, right? Using this principle. Okay. And if we look at this 10 volt source, this voltage minus this voltage is equal to 10 volts. So the voltage of this node is the voltage of this minus 10 volts. Let's generalize this principle. I have already discussed this diagram and how to write Ohm's law using node voltages. We have discussed it in the previous class when we talked about nodal analysis first. So we will combine this together to get a situation where a voltage source is in series with resistance. How will that work? We have a voltage source Vs connected in series with resistance R between node with voltage Va and another node with voltage Vb. Our objective is to find out the current Ia in terms of Va, Vb, Vs and R. We will do that by applying Ohm's law to R. To apply Ohm's law to R, we need the node voltage of the left node of R. Let's call this voltage Vc. Using this approach that Vm minus Vn is Vs, I can say here Va minus Vc is Vs. In other words, Vc is Va minus Vs. And using Ohm's law, Ia is Vc minus Vb by R. For Vc, I can substitute this expression to get this equation. Similarly, if I want to express Ib, the current flowing in the opposite direction in terms of node voltages, I would write Ib is Vb minus Vc by R. Using this equation of Vc, we get this expression. You can see that in our final result, there is no Vc. So it is not necessary to assign a voltage in the intermediate node. We can just tell what the voltage is by observation. If we are at the plus node of a voltage, and from there if we go to the minus node, the voltage will drop by the amount of Vs. So when I go from plus node to minus node, the voltage here will be Va minus Vs. This is Va minus Vs. So if we remember that principle, it is not necessary to assign the voltage Vc. Okay. Now we look at our circuit. We have assigned V1 voltage to node 1, and as I mentioned in the previous slide, that we will treat both branches as resistive branches. Case 0 voltage source is not treated as a voltage source branch, it is treated as a resistance branch. Okay, so I will need the voltage at both ends of 4 ohms. I will also need the voltage at both ends of 2 ohms. At this node, I go up from the reference to this node and the voltage increases by 12 volts. So this voltage is 0 plus 12, which is 12 volt. If I look at this node, I start from node 1 with a voltage V1 and go down by 10 volt. So the voltage of this node is V1 minus 10 volts. Okay, we can now write the node equation at node 1. There are 3 resistances connected to node 1, 6 ohms, 4 ohms and 2 ohms. All the currents through the resistances are leaving the node. So for node 1, the current leaving through 6 ohms is simply V1 by 6. The current leaving through 4 ohms is V1 minus 12 by 4, this current. And the current leaving through this 2 ohms is going downward, which is V1 minus 10 by 2. There is no current source connected to node 1, so right hand side is 0. You can see that if we had assigned node voltage to each non-reference node, we would be dealing with 3 unknown node voltages. Now we have only 1 unknown node voltage and 1 equation. If we solve it, then the result is V1 equal to 8.73 volts. It may appear a little bit difficult at the beginning, but if you do practice and get used to this concept, it's really very easy. Now we look at case 2. In this circuit, we have 3 non-reference nodes, 1, 2 and 3. Again, if you look at node 3, there are only 2 circuit elements connected. So we will not assign any voltage at node 3. We remove node 3. We assign 2 node voltages at node 1 and node 2. At each node, there are 3 circuit elements connected. If we look at node 1, in addition to the 2 resistances, there is a voltage source. And if we look at node 2, in addition to the resistance and current source, there is a voltage source. So it is not possible to write node equation either at node 1 or at node 2. And you can see that this 3 volt voltage source is case 2 and this 7 volt voltage source is case 0, with this voltage being 7 volts. Okay, so we cannot write node equation at node 1, we cannot write node equation at node 2. However, we need 2 equations to solve for V1 and V2. How to do that? Let's see. In this circuit, we will form a bigger node by combining node 1 and node 2 together. The bigger node will be called supernode. So we combine node 1 and node 2 to form a bigger node which is known as supernode. This looks like a supernode. Okay. Now supernode can be treated as a regular node. We can write node equation at any node, or we can write KCL at any node. Similarly, we can write node equation or KCL also at the supernode. If we look outside the supernode, we see there are 4 circuit elements connected. The 4 ohms resistance, the 3 ohms resistance, the 6 ohms resistance and the current source. There is no voltage source connected outside the supernode. So we can write a node equation outside the supernode. Let's write that. For the 3 ohms, the current leaving supernode or node 1 is V1 by 3. For the 4 ohms, the current leaving the supernode or node 1 is V1 minus 7 by 4, this term. And for the 6 ohms, the current leaving supernode or node 2 is V2 by 6, this expression. and on the right hand side the current source term is negative because it is leaving the node. So we get one equation by combining both the nodes into a common supernode. We need another equation. Let's see how we get the other equation. If we look inside the supernode, we observe the voltage source. And for the voltage source, we know the plus node voltage minus the minus node voltage is equal to the value of the voltage source. So V1 minus V2 is equal to 3 volts. This is our second equation. We now have two equations for the two unknowns. If we solve them, we get the value of V1 and V2. So what is the principle for handling case 2 in nodal analysis? First, we form a supernode with the voltage source which is connected between two non-reference nodes. And how do we get the two equations? First, we get one equation by applying node equation outside the supernode. Second, we get the other equation by looking inside the supernode where we have a voltage source. So outside the supernode, node equation gives us one equation, and inside the supernode, the voltage source gives us the other equation. So we have discussed all three cases of voltage sources in nodal analysis. By correctly identifying the case and handling it with the appropriate technique, we can solve any circuit by using nodal analysis, whether the circuit contains voltage sources or not. Thank you. That is all for today.